Okay, so today we're going to start on chapter 21, and we're going to finish multiple regression. Now, some of you may wonder about the summary problems and the practice problem I asked you to do. So I think this would be, since your exam's coming up, we have just 3 more classes, so it will be a week from this coming Thursday. I thought it's a good idea for you to do this on your own, and I know some of you haven't had a chance to yet, and I'll post it on Compass, the filled-in version of it, because it's a good way for you to, it's good practice problems for chapter 20. So that's on page 80, and then we're going to finish part 5 today on multiple regression, and then we're going to have 2 days to do part 6. So let's get started. All right, so what we've done so far is we've looked at a hypothesis test, a chi-squared or an f-test, for the collective effect of all the slopes. And once we do that and find out that at least one of the slopes is significant, if we reject the null for the collective effect of all the slopes, our null is that all the slopes are equal to 0. We reject that. Now we know at least one of the slopes is significant. Then we can do z or t tests on the individual slopes. And that's what we're going to do now. All right? So remember that these are not the same slopes as in the simple regression, right? The multiple regression slopes, just to refresh your memory about what we did, they're referred to as the partial slopes because they're the slopes that explain the part of y, what we're trying to predict, that's left after the other x's in the model have already done their part in predicting y. So if the x's are uncorrelated with each other, then they're the same as in the simple single regressions of each individual x predicting y. But when they're correlated with each other, then they're going to be different. All right. So now, let's see. What are we going to do here? So now we're going to do these z and t tests for the individual slopes in our multiple regression model. The same exact way as we did for the simple regression. The only difference is we're going to adjust the degrees of freedom. All right? And just remember, I just want to remind you that you can't use the t test when you test the collective effect of all of the multiple slopes. When you do an overall test, the f or the chi-square overall test, right? But we can use it for the individual slopes in the model. So that's what we're going to do now. All right, so first we're going to do it just, if your sample size is big enough, you can, the z and t, with big enough sample sizes, give you the same results. So first, since z is simpler, let's just do the z first, and then we'll do the t. All right? So what are we going to do here? We're going to be using the same example, homework and exams. This is the multiple regression predicting finals, and we found that we rejected the null that these are both 0. So now we're saying, okay, if we rejected the null that they're both 0, then either this one or this one is non-zero, or maybe both of them. So let's just start with homework, okay? So we're just going to do a simple test on homework. So our null is that the homework slopes equal to 0 in the population. Just in our sample it's non-zero, but that's just due to the luck of the draw. And the alternative, H alternative, is the slope is not equal to 0 in our population. That's the one-sided, two-sided. Isn't that two-sided? That's like a two-tailed alternative. We could do that, or we could do an alternative. Now we can do a directional alternative because it's just one slope. So you can have it either be, your alternative can be directional. In this case, I think it would be what? The homework slope is going to be directional. So do you think I should put greater than 0 or less than 0? What do you think? First of all, in our sample, we got a positive, right? But we predicted that homework would be positively correlated with final. don't you think? Do you think homework's going to help you or hurt you? Help you. So it's going to have a slope greater than 0. So so this could be your directional one, right? And that makes more sense. But you can see we can just switch back and forth. We should decide which one we're going to use ahead of time, but if we have to switch afterwards, we can. Okay, so those are the alternatives. I think it makes more sense to go with, oops, look what I just did. What should that be? One tail. One tail. Thank you. One tail because it's directional. We're just going to look at the area on one tail. All right, so now the null means, all right, the null is kind of, what it means is this. Let's just think about what the meaning is. This null, right here, this null, saying the slope for homework is 0. It means that once you control for exams, once you take into account exams, that knowing someone's homework score doesn't help you predict their final score. That's what it means. That once you look at it, just becomes insignificant once you, I mean, exams we think have more predictive value, but the null says that adding homework doesn't have any predictive value. Okay? The small positive slope, this is saying in our sample, is just due to what? The luck of the draw. Remember, the idea is that this is a random sample from what? From a much wider population, from like 2,000 or 3,000 Stat 100 students. And the null says that even though this is 0 in our population, we happen to just see this small slope in our sample. Does that make sense to everybody? And it's just due to the luck of the draw. That's what we're doing here. All right? All right. So even though we saw that homework alone, when we did the simple, is a good predictor of the final by itself, we had a bigger slope. Remember, we thought that it might not add any extra predictive value after we already have homework in the model. Okay, so now we have our same z test that we usually do, your observed slope minus the expected slope under the null. And what's the expected slope under the null? What's that going to be? I can cross it out because it's always going to be in the 0. So it's really just our observed slope over the standard error for the slope. Now, it's really tedious to compute these standard errors when there's multiple x's. They're not the same as in the simple one where we did it. So we are going to let the software do it for us. It's too tedious because you have to like think of the standard errors after you can partial out all the other, it depends on what is left over after the variation left over after you subtract off the effect of the other variables. All right, so this is, we got our chi-square. This was our overall test. We did that before, and we saw we have significance. Now what are we focusing on? So this was from the previous time. Now we're focusing on the homework, so let's look at homework. So that's this variable right here. And, oh, sorry. I don't have to go that far. So this is what we're looking at now. And this is the slope right here that we got in our model. This right here. And this is the standard error the computer computed for us. Okay? And generally when you use a z-test, you don't use that adjusted SE plus. So this is what we have. Now we want to calculate the z statistic. So calculate z. It's just going to be like just what we said here. So z is going to be equal to our observed slope, 0.1641, minus our expected, which is just 0, over the standard error, 0.07223. And that's, I got 2.27 rounded. And that's our z, so we can put it in here. All right, any questions so far? This is just Stat 100 stuff, observed minus expected over the standard error. And it's just a z-score. All right, So how do you think we're going to find the p-value? Well, what I'm going to do is just mark as a z-score. We have a z-score, and now we can say a slope. And in the middle is 0, right? And for both, we expected a slope of 0. And as a z-score, we got 2.27. So this is 2. So 2.27 is going to be about here. So that's z equals 2.27. And of course, as a slope, what is that? That is 0.1641. And we just want to see how, this is what we expect. This is our expected. And this is our observed. And we just want to see if this distance, this is our distance as a slope, this is our distance as a z-score, and basically what we want to see is how, when the null is true, and in the population the slope is really 0, how likely it is to get so far away from the non-zero slope. So far away. We really didn't know where to place it on the normal curve. We didn't know where to place this 0. This looks like a very small number. We thought, oh, that looks so small. But once we change it into a z-score, we can see how far away it is. And then we can compute from what we'd expect. And then we can compute the likelihood, the probability, if it's one-sided, of seeing this, if it's one-sided, if we know that it's going to go in this direction, this is going to be our p-value. And if it's two-sided, of course, and we don't know whether it's going to go in this direction, that extreme, or in the other direction, equally as extreme, which would be right here, what is that? That's negative 2.27, and that's your positive. So if it's two-sided, we have to count both tails, right? We'd have to do, for the two-sided, we'd have to do both of them. We can do the one-sided, we can do both of them. All right? So what do we need to find? You could either look on the p-value calculator, but we don't have that. So right with us, actually I did look at it, but if you just to refresh your memory, what you're going to have on the exam is just this normal table. So what do we want to do? We're going to look at 2.27 here, and 2.27 is right here. So somewhere between 97.56 and 97.86, right? Between z and negative z will give us that middle area of 97.7. 97.7. I actually looked it up, and it was 97.7 on the p-value calculator. So this is 97.7%. Any questions so far? All right. So now, depending on what's the question mark, z and p. All right. So for the one-tailed test and for the two-tailed test. All right. We can do the two-tailed first. So if we had for h alternative that the homework slope is not equal to 0, then we just would have what? P would just be equal to 100% of the curve minus 97.7. So that's equal to what? Just that together would be equal to 2.3%. That would be both tails together. 2.3, which means each one has to be half of that. So this is, right there, is 1.15%, and right there is also 1.15%. Okay? So this is also 1.15%, that and that. So for our alternative that's one-sided, one tail, and that's a directional one, is greater than 0. We're just looking there. So then we have half of that. All right, so which one should we fill in? I would have to tell you. Let's say I told you this is for one-tailed. For one-tail alternative, one-sided, then I would fill in this one. And if I told you 2, you'd fill in the other one. Okay, any questions on that? So now what do we decide? What do we conclude? Well, we have to set a significance level to reject them. This is, to think about it without that is just to say, okay, the probability that we would see such a big slope as 0.1641, if it didn't exist in the population, it could still happen, and that probability is very small, 1.15%. Okay, for the one-tailed. That's what you so if ahead of people want a cutoff, like you have a cutoff between, instead of telling you that your overall score was like 94%, I just said you made the cutoff for an A. That's what a cutoff thing. So instead of, it's a broader, it says, oh, you got an A. Okay? But if you want to know the actual score, there you have it. That gives you all the information you need. But then if people want to say, okay, I'm going to decide significance, I want a cutoff. So for, for alpha, what? For a significance level of alpha equal to 0.05, then, yes, we would reject the null. But if we wanted a significance level of 0.01, no, we'd have to be a little bit further out. So for alpha equals this, 5%, we're going to reject the null whether we do a one-sided or a two-sided. We'll reject the null that homework slope is equal to 0 and conclude what? That it's either greater than 0 or not equal to 0. We'll just conclude that it's significant. Conclude that it's significant at the 5% level. Significant at alpha equals 0.05, but not at what? If you wanted to set your alpha at 0.01, it's not. Does that make sense to people? Any questions on that? Yes. Like that? Is that what you mean? That? Move it up on the screen. What are you trying to look at? But not? Okay. I can do better. I can do this. No, this. Go to inside. Why isn't it doing that? It won't let me zoom in anymore. Oh, there it is. Is that what you want to see? This says, but not at alpha. This is an alpha. So it's significant at alpha equals 5%, but not at alpha equals 1%. Does that help? Okay. And you understand why. Because this is less than 5%, even two of them together, but it's not less than 1%. All right, so let's go back wide and go to the next page. And now we're going to look at the t-test and do the same thing. Remember, the t is generally what software does because it's precise, more precise. And so generally it's what and you're going to get a slightly bigger p-value using the t. You need more, you have a little more, you're acknowledging that you don't know these standard deviations of the population, and you're using your data to estimate it, and that, so you're going to have a little bit fatter tails, which means bigger p-values. And you also, generally with the t, you use the SE, you always use an adjusted standard error. We could use that with the slope, but generally people don't. All right, so now, this is the exact same thing. There's just these degrees of freedom change from this. Remember it was n-2 when we did simple slopes by themselves? Remember that? Raise your hand if you remember that when we did the t-test before, for linear regression, with just one slope, it was always n-2. That's because you had two parameters. But now the formula is really n-p for the degrees of freedom. All right, so what we're going to do is we're going to be using the standard error for the slope, and we are going to be tweaking this. We're now going to have the degrees of freedom of n. We have 107 minus our parameters are 3 because we have an intercept, remember, a beta naught, a beta 1, and a beta 2. So this means 3 parameters. 3 parameters. So this degrees of freedom is equal to n minus p. And what is n? Remember, n was equal to what? 107 students. So our parameters equal 3. And so that's where this n minus p, that's where this degrees of freedom 104, because we are going to be looking at a t curve. And there's a whole family of curves, and this is the one we're going to be looking at. Instead of, we always looked at n minus 2 because we had 2 parameters when we just had an intercept and 1 slope. All right. Now, that's the idea here. So your error degrees of freedom are n minus. This is the same as the error degrees of freedom, the degrees of freedom 2 in your F test. All right? And here it is here. All right. So now, so in other words, this relationship, this is our, let's just look at this. So now we're looking at the same, we're looking right here, the same slope, but now we're going to divide by this standard error, which is plus here. So that means it's a tiny bit bigger than what we had before. So if you want to look at that, that's what I showed here. So our standard error is plus is going to be multiplied by what compared to our old standard error? Well, our old standard error was equal to, on the previous page, was, so it's either, the choice is, do you want to multiply it by, a bigger number here, so this is bigger than 1, so we're going to multiply this by n, which is 107 over 104. And remember what this was. It was from the previous page that we used before, 0.0. I'm sure you don't remember, but you can just turn back and look at it, and I'll just copy it down here, 0.327. So that's just, excuse me, that's what this one is. I just copied down that. What we, I don't remember it. I got to go back and look at it. All right, it's that. 7223. All right, so remember that. 7223. Okay. And we multiply those two together, that's what we get. Right? So that standard error plus is that. Right there. That times that, and that's equal to, if you multiply, substitute in that, you'll get 0.07327. You can see it's a little bigger. I mean, these differences are kind of annoying because they're so small, but I just want to alert you to them, the difference. All right, so don't get hung up on that. Let's just keep going. And now we're just going to do the same thing we did before. What do you think? The degrees of freedom is the number of parameters in the model. N minus the number of n minus p. All right? And you know how you can think about this? Why did it change? Why did it change? Because it's taking into account all the other slopes in the model. So that's why you don't just have n minus 2. You have to have n minus all the other ones too that you add in, which is simple regression. You just had 2 parameters. But every time you have to add, your slope is taking into account. Remember, it's different. It's adjusting for every parameter. So it's not just n. You have to subtract off p for all your parameters in the model. And in this case, it's going to be n minus 3. So think of it that way. It's not the same. That's why you're doing it. Okay? So calculate t. We'll do the same thing. So t is going to be equal to our slope. This part is the same minus the expected slope. But now you're just going to have a slightly different standard error. This is a little bit smaller. So we're going to get a little bit bigger. So you're going to get a little bit smaller than what we got before. So this is 2.24 as opposed to before, what did we get? 2.27. Okay, so that's all. So now the degrees of freedom, we said right up here is 104. And now mark T and P. So let's say this was a T curve, all right? If it was a T curve for 104 degrees of freedom, looks very much like the normal curve. You can barely see the difference. But now we're going to mark on here, right here, is, this is, we're doing, now that we have a T and now we have the slope, it's exactly what we did before. As this, we have a 0 and we have a 0, and that's our expected slope. And this is the same thing we had before. This is our observed slope, which is 0.1641, and that's our observed slope. And once we translate it into a T, instead of, it's just doing the exact same thing, but we get a slightly smaller than the Z. But these tails are also slightly fatter. Okay? So we're going to do, is the p-value using T, it's always going to be bigger. So how are we going to figure it out? Well, we are going to have to look at, we want to get this p-value for the one-tailed, and for the two-tailed, we're just going to do this. And we'd get both tails. All right, so since we don't have a, we'll just go to our p-value calculator and get it. Any questions so far? All right, so the reason that we have to go to the calculator is because 107 degrees of freedom, I didn't give it to you. So if I'd have to give it to you here. Look, it only goes up to 25. So it's going to be very similar. This is a very, with 100, that's a lot of, gets very close to the Z. So we'll look at this, and let's go to our calculator and just go here, and where is it? Right here. So we want the T distribution, and we have 104 degrees of freedom, and we have 2.24, and if we want just the right, we can compute the p-value, and we get 0.13 for the p-value, 6. Okay, that's for the one tail, right there. Compared to, we had 1.15. All right, and so for the two tails, you can see you're just going to double that. Any questions? So let's just go back and do that. So, all right. So what do we have here? So now, so we just said the P right here is 1.36%. So that's bigger. And this, of course, is going to be 1.36% too. So if we want to find T and P, T is going to be the same, but P, let's just do it for one-sided alternative. Okay, and then we would have what? We'd have 1.36 here. That's double. All right? And now, so the question is, the p-value always is bigger. It's fat because T is fatter in the tails. So it has a little more area. Also, your T is a little closer. But the real effect is, and as you go further out in the tails, it's more important. the effect is really big. So if you're looking for very, very, very tiny p-values, if you want significance, extremely strong significance, p-values less than, 0.001% or something, you're going to get a big difference when the further out you go in the tail. Okay? So yes, especially the further you go out in the tails. Especially the further out in tails you go. Like sometimes you do these, especially in scientific experiments, you want to notice, really, really p-values very, very tiny. Then it would make a bigger difference than if you're looking at 5%. All right, so now let's look at this. Now, how about confidence intervals? Confidence intervals. These relate to confidence intervals. And let's look at how we would do this, the z compared to the t. So remember, confidence intervals are just looking at like a 95% confidence interval. That's what these are. Let's just draw the picture so you can see what's going on. So for the z, let's draw a picture of the z first. So if you have the z curve right here, z, and now you're going to draw a normal curve. And when we look for a 95% confidence interval, that means we want 95% in the middle. So what we're looking for is the critical values of z, between z and negative z, that's going to give us 95% in the middle. And usually we estimate it as 2, but this is being a little more precise, so that is 1.96. Okay? So so that means that the two tails together are going to be 5%. So let's just say it looks like this and that. And then you have, you can call them the critical values. You can say you have z star equals negative 1.96. Usually use the positive one, 1.96. Now that's the same as, think about this. This is 95% in the middle, but if you're looking at the tails, that means 2.5%. So together, it's the same, a 95% confidence interval. If you're outside this range out here, that's equivalent, this is 0. So if your 95% confidence interval does not include 0, like it doesn't here, that means it's equivalent to a two-tailed test at alpha equals 5%, or a one-tailed test at alpha equals 2.5%. Say it's the same to a p-value of 5, less than 5%. We'll look at that. Now let's look at, hold that thought. Do our confidence intervals agree with our significance test? I'll write that down in a minute. I just wanted to show you while I was drawing the curve. So now let's look at the t curve, and it's going to be a little bit fatter. And now the t, there's not just one curve. This is why t is more complicated. You have to look at a t curve with the degrees of freedom equal to something. So here the degrees of freedom will be equal to, what? 104. And that's why it's going to look very close to the normal curve. So let's draw it. I wouldn't be able to see the difference at all just by the naked eye, but all right. And now our t is a tiny bit smaller. Here's our critical value. So instead of being 1.96, it's just a tiny bit smaller. That's always true because you're dividing by a bigger standard error. So now we have the critical values, t star, for this particular degrees of freedom, and it's 1.983. How do we get that? And this is negative 1.9. Excuse me, I just spoke wrong. I just confused you. I'm very, very sorry. The t, look, I was thinking of the t statistic is going to be smaller. I made that really bad mistake that I tested you on. The t critical values are going to be bigger because, remember, If it's fatter in the tails, that means smaller in the center. I have to go further out to achieve the 95%. And I'm very sorry I did this. So these are bigger, and let's write that down so I won't make that mistake, and you won't make that mistake. So I'm just going to write that down right now. These are our critical values, and I'm very sorry. So I said what? The T critical, right, is going to be bigger. For the same 95%, it's going to be flatter. I have to go further out, right? Further out to get 95% in the middle. I need stronger evidence to reject the null. So the T critical is going to be bigger in absolute value. That's 1.983 is bigger than Z critical of 1.96, right? But, and it's really the same reasoning, that's your significance level, but the T stat, and this is what I confused, it's very easy to do, is actually less than the Z-stat for the same data. And remember, that was 2.24 was less than 2.27 in our sample. This is our sample statistic. Does this, maybe, does that make sense to you? Remember, we want to leave 5% in the tails, right? We want, when we have 95% in the middle, we want 2.5 and 2.5. So if the tails are fatter and we want 5% still in the tails, we have to go further out, right? These are going to be bigger tails, fatter, so you have to go further out. F and T are fatter in the tails. F and T, fat and tails. A lot of people like fat and tails these days. When I was, I'm just making an illusion, some way to remember it, right? Okay? So a lot of people like F and T, and a lot of people like being fat, looking at people who are fat in the tail, right? For different reasons, but maybe, I don't know, some mnemonic to remember it, fat in the tails, okay? So if you're fatter in the tails, to get the 95% in the middle, you're going to have to go further out. So those critical, that means more evidence. You have to go a little bit further out. Not 1.9. Our confidence interval's going to be wider. All right? So this is 2.5%, and this is 2.5%. And this is fatter in the tails. All right, now, do our confidence intervals agree with our significance tests? Why or why not? So let's look. Our significance test rejected the null, right? So do our confidence, that means we don't think the null, and the null is right here at 0. Our significance test said we were outside that range. Do our confidence intervals say the same thing? Do our confidence intervals say, hey, if we landed, do our confidence intervals say that our particular sample landed out here, so that if we go over, landed somewhere in here, so if we go over 1.93 here, or 1.96 in terms of z-scores, we don't capture. We do not capture. So how do you compute these? Wherever your sample landed, and our sample was positive, so it landed over here. So it's like a one-tailed test and if it says, okay, what do we want to do? We want to go over, in terms of a slope, we're going to multiply 1.93 times your standard errors, but in terms of, like, let's just stick right here with this is much easier. Let's just stick right here in t-scores or z-scores, and we just go over 1.93. This is 1.983. If we're bigger than that, you see, we don't capture 0 in there. So what I'm saying is, if you look at these two slopes, is 0 included in it? If we were here, if we had a confidence interval, if our z statistic or our t statistic was on this side, then when we go over 1.96, we're going to include 0. And then we wouldn't reject the null so they're totally equivalent. So we can write this down, but these didn't include 0. Why am I doing the exams? We haven't even gotten to that, but that's a very stronger effect. Look how far away from 0 that is. That really doesn't even come close to including 0. But right now we're just looking at this and this. All right? And so, yes, it does agree. Why? Because our 95% confidence interval for both these tests do not include 0. And both those tests rejected the null at alpha equals 5% for the two-tailed and which is the same thing. Do not include 0. So how can you think of this? Since they don't include 0, we're confident that 0 is not, it's not that our population slope isn't 0. We're 95% sure it's in this range, and it's not 0 included. 95% sure it's in this range, and 0 is not included in that range. So that's the same thing. So our 95% confidence intervals do not include 0. So it's the same as, rejecting the null that this population slope, the slope in the population, is equal to 0. So it's the same at what level? It's the same as rejecting this. I'm saying the same as rejecting the null, rejecting a two-tailed alternative at 5%, at alpha equals 0. At 5%, that's alpha equals 0.05. How about a one-tailed? It's the same as what? Rejecting null. If you're doing a one-tailed, what? Not alpha equals 5%, but alpha equals what? 2.5%. So if I had room, I don't, but I'll write it right down here so you can put in your notebook if you want. It's the same as rejecting the one-tailed, the directional alternative, that the slope is greater than or equal to 0, not just not equal, at alpha equals 0.025, 2.5%. And that's 5% for the one-tailed, because I hope you see it just from the picture. It's so much easier if you think of the picture. 5% in two tails is like a 95% confidence interval, or it's 5.5% in one directional. Okay? And if we'd gotten a sample slope, if you thought it was a negative relationship, it would be less than 0. Any questions so far? All right. The only thing that's different is your degrees of freedom. This is exactly like what we did when we tested one slope in a simple regression. So what's changed? The degrees of freedom. It's always been n minus p. It's just with one slope. You have p. It's two parameters. So unfortunate that p is used for the p-value, which means probability, and p is also used for parameters, number of parameters. Okay? Questions? All right, I think we're done with that. That's our next thing to do. So our next thing to do is let's think about adding a third variable in the model. And if you go on and take something like Stat 420, this is what you're going to be doing a lot of model building, like seeing how each time you're going to learn procedures to add more and more variables and to see there's lots of different procedures for doing that. And so I'm going to give you the basic idea of what happens, why you can't just look at R squared and just go by that. All right? So it's a little bit more complicated when you add parameters into the model to determine what statistics to use to determine if you're really getting a significant effect. So that's probably so much easier. If you just go through an example, you'll see what I mean. So Z and T test showed that both the homework and exam slopes are significant. If you look, the homework was even the exams were even more significant. Look at the p-values here for exams. So now, we didn't go through the test, but this is even more significant. And so now, as you'd expect, we're going to keep them both in the model. Now the question is, how about adding a third variable? Would that help my model? Well, so I'm wondering if adding a third predictor variable will significantly improve the prediction for the final. Okay? So in the past, we used to have, in Stat 100, this data set comes from when I first started, before I was teaching Stat 100. The previous person was teaching, and this was, well, actually, I did teach back then, but this wasn't a semester I taught. Okay, so we had labs. So I thought, well, computer labs, we have much smaller sections, and so we thought, okay, why not add your lab score in? So I added labs as my third x variable. Now, how do you think that would change your r squared? R squared, remember, is just how close, it's the correlation between your predicted final scores and the actual ones. So don't you think that just adding any parameter, it can't make r squared go down. Every time you add a parameter, it's going to predict your sample better. If r, the only way it wouldn't do anything is if I added something which totally had no predictive value for finals. So it has to go up or stay the same, even if it was negatively correlated. It's r squared, remember? It's going to go up. It's going to give you more predictive value, like if it was the number of hours you party per week. That would mean your finals would probably predict your finals going down. That gives you more predictive power. We're going to do now. So what I'm saying is every time you add a parameter, it costs you, it's going to make a better prediction, but that doesn't mean it's going to fit the next sample better. It doesn't mean it's going to fit the population better. It's just going to, it could just fit the sample better. All right. So that's what so I added labs, and I checked, did r squared go up? Now this is really small here, so I'm going to zoom in a little bit for you. Okay. So I checked r squared and saw it went up, but look how little it went up. Look how little it went up. It went up from 0 point, right? That's how tiny it went up. So so r squared, but how am I going to judge if it's if I should keep labs in or not? How am I going to do that? Because, well, look, the number of parameters is equal to 3 here. There's a beta naught, a 1, and a 2. So our parameters are equal to 3 here. Now I added a parameter, labs, so it went up to 4. Now, so my r squared went up, but let's look at other things. The f went down. The f statistic went down, right? So where's my f? The f is right here. That went down. Why? Remember, big values of your f statistic are strong evidence against the null. But it went down, even though r squared went up. Why do you think that went down? And that went down from 32.43 to 21.42. Because remember how we compute it. So f is equal to r squared. Let's do this together. And here, are you getting bored? I hear it's yawn. Are you getting totally bored? Statistics can get so tedious, but I just want to show you this. So you have r squared over 1 minus r squared. Okay? So, so this part will be the same. Right? And here I'm going to have the same thing. But now I'm going to multiply by what? By 104 over 2. And that's where I get the 32.43. All right? Now what's happening here? This part's going to be very much the same, except we'll have a 2 here and an 8 there, right? So that's not going to change hardly anything. 0.38 of r squared going up by that little amount is not going to make much of a difference. But what is going to make the difference? Now, look what I have. I've added one more parameter, so it's n minus 4. So I get 103. That still doesn't make that much of a difference, a little bit. But this makes the big difference. You now have 3 parameters. So when I divide by 3, that's going to make a big difference. And I get, here I got 32.43 as my f. And here I got what as my f? 21.42. So f went way down. And the way I want you to think about this is that when you add every parameter, and as I said, I could get 100% correlation. If for each one of you, I just picked whatever multiplied your multiplier for you, you would have a variable specifically for you, and it would be when you were in the model, it would just be your homework score divided, your final score divided by your homework score, and then perfectly predict it. I'd have an r equals 0, but it wouldn't fit. It would just fit the peculiarities of this. So the idea is this, and think about this. Basically, this is the way you can remember it, is that each time, and look what I just did. I have no idea how that happened, sorry. I must have touched one of these things. Let me see. Is that doing anything? No. Rotating. Oh, here it is. Sorry. So each time you add a parameter, to the model, r squared does go up. So checking r squared is not going to help you unless you have the same number of parameters. But it costs you a degree of freedom. Okay, it costs you a degree of freedom. Should be an exclamation point. So you better add a parameter that's worth adding. Labs was significant on its own, and it looked like a great parameter for me to add. It wasn't like a hinky-dinky little parameter. It looked like a great parameter. So why did it do this? And look what it happened. If you look at the significance, I mean, you're going to have to look at all this when you really do this. You look at like what happens, and look what happened. Yes. Let's just look. So we look here, and the first thing you notice is what? That these right here, let me zoom in. I know this is tedious and everything, but look. These were both significant. Homework we just saw it, had a value, a small p-value. Like right here, 1.36. Now, you add, that was actually 1.26. I don't know, didn't we just do that? It was 1.26? I don't know why I can't, but it was small. And now we add a parameter, and it's not significant anymore. Look, it's 8%. And look at labs. That was, I didn't show you, but that was completely significant on its own. And it's not significant. So how can this be? Homework is significant on its own. Labs is significant. We can look at it in a minute if you want. But I put them both in the model. They're not significant. So why did labs, r squared did not, let's read this. And so it says, just trying to focus it for you guys. There. R squared did not improve enough to warrant adding the third variable, so we're not going to add labs. Labs are not significant, as you can see above. But why did adding labs make homework change from being significant at 1.36 here, I guess it's 1.36 here, to being not significant, 8.47? Why? Could this be a mild case of our multicollinearity of when two variables are very correlated, like left foot and right foot, that when you put them both in the model, you can get they can both become non-significant? Because any linear, when they're very correlated with each other, they're saying pretty much the same, very much the same thing. And so you get screwy results. So let's check if they're really correlated. How would we check if homework and labs are correlated? This is these ones down the diagonal. Homework and labs would be what little square in here? See how it would be this right here? They're very correlated with each other. So when they're very correlated, beware of that multicollinearity. You're very correlated. This means that both slopes can be insignificant when included, even though individually both are significant. That doesn't mean we should throw them both out of the model. All it means is that we can't do a good job of estimating how much of the prediction should be based on one or the other because they're both predicting almost the same thing. Does that make sense to people? All right. So I know that's a lot to swallow. Let's just, so now we realize, okay, we don't want them both in the model. So we have a choice. We have a choice. And basically, this will be the end of this model building here. We have this choice. We don't want homework and labs both in the same model with exams, right? We don't want that. So what are we going to do? Let's compare two models to each other. Okay, so let's compare two models. So this model has what? Labs, they both have parameters equal 3. So let's write down their models. This one has what? The labs, and this one has the homework. They both have the exams. All right, so this is final, predicted final is equal to some intercept plus beta 1 times labs, let's say that's x1, plus beta 2 times exams. That's our model 3 parameters. 1, 2, 3. Now this one's going to be our other model, and that says beta naught plus b1 times homework plus beta 2 times exams. So the only difference between these two models is these two. They have the same number of parameters, so now we can check R squared. We can, because they have the same number of parameters. So now when we check R and R squared, here's R, and when we square it, we see this is the better model, because R squared is higher. Okay? So we can see that, so we'll see which R squared is higher. R squared is with, what is it, homework. That model is greater than R squared with labs. And both models have P equal to 3. Same number of parameters, so I'm just going to go with the one that has the higher R squared here. So go with homework model. Homework is a better predictor than labs when exams are included, because these R squared's higher here. And you'll see that the F is also higher. F should be higher here. This is a better model. So this one's better. Because you also have, look, you also have a higher F. You're going to have a lower errors. It's better on all counts. I mean, if one is true, all of them are going to be true because they have the same number of parameters. All right. Questions. What we're going to do next is fun. Let's just change this to make it easier. You're getting, okay. Look at the SD errors above on the right and the SD errors below. Okay, let's look at this, SD errors, these two, and this. Let's compare those two. Okay, how are they related? This is getting too hard. Too complicated. How are they related? This is just like what you did in your homework, and some people needed help with it. Okay, so this is SD errors, and this is SD plus. So we're going to look at, so we want to know SD errors. This is what how does it relate to SD errors plus? Okay, in this example, how do they relate? This is SD errors plus right here. Right? And this is SD errors. So how are those two related? So this is the plus 8.174, and this is the errors 8.059. Well, now you know you can take 1 over the, but what would you put in here to do this? Well, which one's bigger? SD plus is bigger. This is bigger. Has that plus, and this is going to be the smaller one. So if you had to choose, so should you multiply, the relationship between them is this. You either multiply by n over n minus p, or n minus p over n. So in this case, you'd either multiply by 107 over 104, or 104 over 107. So which one would you choose? You want to make it smaller, so you want to choose one less than 1. This one is less than 1. So this would go in here. That's less than 1. We want to make it multiply, that's a smaller, okay? So that would be your answer. All right. Take a deep breath. It's a lot. Any questions? I'm just getting, I wish I had a drink of water or something. Okay, so, anybody have any questions? I need a break for a second. All right, let's just move on then. This is our summary. Read the summaries. This is fun. This is fun. Believe me, even though it's coming at the end here. All right, so there's a whole other way to do these tests, a completely different way that's just easier, I think, way easier, and it's very useful. And that is simulations or randomizations. So, and often, okay, so let's read it. The Z, the T, Z, F, chi-square, all these are parametric tests. What does that mean? They depend on assumptions that the errors in our linear model are independent and identically distributed like this, normal 0, sigma squared, and that there's a linear relationship between the parameters, each predictor, and the y variable. The randomization test, also called the re-randomization test, has the advantage of not requiring normality. It's a completely new way of doing a significance test called a distribution-free way. You don't have to know a lot to do this. You can just be a kid and just play with it, right, if you could have a computer. These have become super popular because of computer power. When I was learning statistics, we couldn't do this. It would have been so cool. We always imagined doing this. You guys are so lucky, and one of the best things about learning programming languages like R is you can do all sorts of simulations. So this is just a super simple one, and I think you're going to like it. So, it's so much easier. So, instead of computing these test statistics by estimating standard errors, worrying about those n minus 1s and minus p's, assuming these theoretical underlying normal distributions, and they're not like, usually they don't, these assumptions are violated or large enough sample size that the central limit theorem kicks in and all the stuff you learned. We can do this instead. So, here's how it works. All right, so you have the null. That your final exam, let's just look at two variables first, homework and finals. So the null is what? That there's no predictive value. Homework doesn't, there's correlation 0, right? R is 0 between these two, if you just want to look at the positive R. Okay, let's just start with two variables. In the population, in your sample, sure, you see something. In your sample, you see an actual this. We found that. But our null is, in the population, it doesn't exist. So here's how it works. And the alternative is, no, in the population, this is too big to be due to chance. We'd expect R equals 0, but it's too big to be due to chance. We think it's real. So here's how it works. If there really is no relationship between your homework score and what you got on the finals, we could expect to see any of the 107 final scores randomly paired, associated with any of your homework scores. So in other words, we could scramble them up and randomly assign them to randomly assign somebody else's final to your homework score, right? Just might get your own, but chances are you'd get somebody else's, right? And then you compute the R each time for each of those scrambled, and then you look at the distribution of all those R's, and you see how extreme this is compared to the distribution that comes from your actual population. So imagine, let's just do it for these 20 here. So imagine putting all the final scores inside a box, all 107, shaking them up, and this is how bad, by the way, people used to do on Stat 100. If you can imagine, these are the real scores before we came in, and now we teach more bragging points, teach a hell of a lot more, and the scores are nothing like this. So people who think Stat 100 is easy, this is what it used to look like. People used to shy away from it like they do at every other school in the country. That's not going to be on the video because I'll get, but I believe that. I got to cut that part out. That's dissing other schools. I don't really know every school, but okay. So this is actual what they were looking like all the way through. This is what they looked like. All right. So anyways, so now we put them all. So these are your actuals. These are your real pairs. So before we do anything, let's just remember that right here, these are actually paired up right now, the way they are. So these are your actual of the students' paired scores. The actual paired homework and final scores. Actual paired, I'll call it X for homework and X sub I and Y sub I for each I, and I is from 1 to 107. Okay, so these are the actual ones. Now, we are going to then put all these in a box, pretend they're in a box, pretend I scramble them up, so I'm going to close my eyes, and instead of doing that, I'm just going to run my finger down and like, okay, stop. What did I get? 70. So 70 is going to go with the first one. And I'll do it again. I would throw 70 out then and then do another one. Okay, 42 is going to go with the next one. This is just one scrambled. And I do it all the way down and just get 20 scrambled finals. Okay, just randomly. And then I would look at these two. And what are these pairs now? Those are the random pairs, the scrambled pairs. So it's the same X1s, your homework, the same X1s, but now you have Y's that are just random. All right, so now what do? What we do is, let's say we did this 1,000 times. We would have 1,000 R's. They're going to be negative. I'm going to make them all positive. Some are negative, some are positive. I'm just looking at the absolute value. Each time computed from 107 homework and scrambled exam pairs. And then we can make a histogram. And that's what I did here. But let's do it in real life. It's more fun. Because I love, this is the best, this is what I like using computers for. And you can program this in R or anything. If you're in the program course, you can do stuff like this, and it's really fun. Okay, so, and you can do it on our data program and play around with it. So let's just go to our data program so you can see how it works. And, all right, and so now we have to go back to here and go to our data program. And you can do it with this data set if you want. You pull up the grades. You see how much more excited I get rather than looking at all those. This is not boring. This is fun. And it's especially fun to think of models you can do and simulations you can do. It's the best part of statistics, and guys are so lucky that you have the computer power. That's why computer science and stats is just going to rock this world, I think, together. Okay, so now we are going to go to the grades, which is our thing. And you can get all you want here just by point and click and just get all your ideas here, and then you can go and learn a programming language and want to learn R, and then you can do it there too. So we get our regression, and we have our Y variable is finals, right? And here you can get all your ANOVA tables and everything, but I want to do the re-randomization, and I'm doing it with homework. So, okay, so homework, predicting finals. So there's our sample R, 0.3926, right? I'm just looking at just simple regression. And here's our slope. So I'm saying, is this under the null? How weird is that? And so I'm going to do these re-randomizations. And after 1,000 scramblings, computing an R each time, I want to see how this compares. Now, I did it with we do it with capital R, which is the absolute value, because we want it to hold for multiple regression too. So let's check it out. So 0. So far, what is this right here? This is our actual sample, 0.39, almost 0.4 that we got. And so far, not one of the 1,000 got there. So our p-value is 0 so far. All right, let's do some more randomizations. And just, I love how fast this is. Watch. Now it's 2,000. Watch this. See if we get one. If it changes, that means we got one. Let's do it. Let's see. We got one bigger than that. Just watch it carefully. Let me see. So far, 7,000. No. No, not yet. We will eventually if I keep doing this. Come on. It's a very small chance. Oh, come on. Usually, it's just by the luck of the draw. We'll see. Oh, there we go. Okay. You can't probably see it, but there, we got one. So it is possible just by, but look how, now you understand what a p-value is. Look how the chance of it is so tiny. And that's just what's in your notebook. All right? And then we can do the same thing with multiple regression, but we don't have much time left, so let's just understand it was simple, but maybe to do your, okay, let's just do it, and then let's go back to the document camera and fill this in so you can just be amazed like I am by this and love it. Okay, so what are we doing here? So right here, this is our sample. Right here, it's this. This is our observed sample R. Okay, I'm going to say capital R because I want it to be, even if we got a negative, we're counting them as positive. And this is our empirical sampling distribution of R under the null that our R pop is equal to 0. And same here. And here we did get, I got it sooner just by the luck of the draw, so I got a little p-value. So that's what this is, okay? And in the last 2 seconds, we can do exactly the same thing with multiple regression. And I'm just going to show you what we can do here. Okay, so we add another variable. It's so cool. Just think of it this way. Now you have your real homeworks. And these are your actual homeworks. So these are paired up. This is with this. All right, so let's just do the same scrambling. So if we look at all this, okay, and now if I go all the way, this and this are your actual points. So these are your actual, I'll say X1 for homework, X2 for exams, and Y's. These are your actual ones for everybody, the paired ones. But now I'm going to scramble. I'm going to leave these two the same, and now I'm going to scramble them all. So what is this going to be? This is going to be your actual X1s and X2s, but now you're going to have your Y's random. And then I'm going to compute. So we could do the same thing, just put my, put them all in box. Whoop, 72 would be here. Do it again. Oh, 58, etc. And those are your scrambled. Okay, and then what are you doing? For each one, you're computing the capital R, Y, right? How well they're correlated. And we do the exact same thing. And so that's it. I'll go over it again next time. But it's really fun, and I'll see you on Thursday.